Welcome back to High Performance Computing, Advanced Scientific Computing. This is the second part of our lecture 10 on parallels and scalable machine and deep learning. And in the first part, we really gave a relatively, let's say, short overview about how machine learning could work. It was a very simple introduction of machine learning, giving linear learning models, linear in the idea of the weights that we were learning to the linear model. And we picked the perceptron learning algorithm, which admittedly has, let's say, problems with data, which is, not really linearly separable, but it captures the essence of what machine learning does. It changes the weights over time, right? Through iterative learning models, I can change these weights in this particular idea of the model, which was basically modeled after humans in the basically human brain with a neuron. Of course, we have other learning models we will talk about, and I bring a couple of them today, but also basically as part of our practical lecture 10.1 and 10.2. But still, you will see that the basic ideas of labeled data sets of attributes in a vector X, for instance, that was describing our data, and then having the guiding output Y as a kind of class information or label or ground truth, as we sometimes also call it, is something which many machine learning algorithms share. If it is a supervised learning algorithm or supervised learning method, there are also other areas with, basically reinforcement learning or unsupervised learning where you don't have any output to guide you, just the identity, so to speak, in the data itself, where we said clustering can be maybe applied in order to find with similarity measures or Euclidean distance clusters in the data. But essentially now, the simplest learning model in the linear learning model space that you can find is this perceptron, and it does a job if the work is linearly separable. What we did in part in part one, we didn't really talk about much what HPC can do about it. And that's, of course, now should be the motivating more second part here, why HPC has really lots of positive aspects to this topic, which is a large topic. And that's why, of course, I, again, also in this particular part 2 now, where we talk about many different aspects in order to learn really properly about classification, clustering, and regression, I would encourage you to go to a machine learning course, right, where you learn statistical learning theory, which is a bit required to really understand how much data you need in order to fit specific models, where you learn aspects like overfitting, where you learn aspects like validation of models, which is essentially model selection based on different parameters for these models. So it has a huge class of, let's say, elements which I cannot bring across here because we just have, let's say, an HPC lecture here, not a full-blown machine learning course. But the overlap these days, especially with GPUs and deep learning, for instance, is rather tight. And with this, of course, we see machine learning today in the supercomputing centers worldwide as one of the bigger, let's say, users of our systems than it was basically the case perhaps 20 years ago, where basically physics were mostly using, or physical modeling based on, natural phenomena, natural laws of physics were really where the most workload in our systems. So coming back to classification, here we learned about the others before in part 1. Let us now look basically in part 2 a little bit more to classification, and now thinking a little bit more where HPC can actually make a difference. With the linear learning model, you have learned that basically the decision boundary is a very specific element in data sets. And when you see, again, and coming back to our simplest examples with the red points and the green points from part 1, you could say, okay, the line was giving us the idea, but how do I know that this line is the best? Why it's not this one, right? Or the other one that you see here. These are all valid decision boundaries, because essentially, when we learn from these examples, the red ones and from the green ones, you will see all of these lines classify them correctly. I think there's no doubt in that, and you see that. The point, however, what classification is all about also is, of course, we want to have future data elements right. Once again, future unseen data, we want to classify right. We're not learning this to explain the data. That's not the goal of machine learning. We're learning this to create a system that is able to tell us if there's a new point landing here, landing here, landing here, landing wherever in the space, what is now essentially the class label of this particular new point. And then you are at the idea of machine learning, which we say out of sample performance, generalizing well out of sample. That is what basically our models want to do. This is in sample, right? In sample data we learn from, we create the model. But the truth is, and you see here two examples of these and these fellows, which basically based on this example are our new unseen data or future data. And there we want to do the answer right as best as possible to say, well, this is behaving more like a red point and this is behaving more like a green point. Now, this alludes to one of the techniques also here in this particular visualization, which is a very sweet technique, very robust. It has just a couple of parameters, still does a very good job, especially if you combine it with so-called kernel methods, which is a space of support vector machines. So still used today, although deep learning has many more advanced models, which basically outperforms the support vector machines here and there, but deep learning also has hell a lot of parameters. Here, support vector machines has usually just a cost parameter and the kernel method parameter, which makes it a very robust model to switch and to tune. And if your data set basically is, still relatively few data, chances are that support vector machines are better because deep learning models need very big data sets to really learn from, while support vector machines can actually do the job still quite good if, let's say, you have just moderate or small data sets, which makes it also, again, robust. And one example where we basically use that particular support vector machine techniques could be to differentiate here in a multi-class setup, basically of the ground, cover or land cover of short. You see here basically a satellite image, and we want to identify with classes what each of the pixel in this image entails. So you would say this is particularly water, this is a tower, these are trees, these are vegetation. So based on all these different colors, we want to create a machine learning system, which is not anymore a two-class system you have seen before, right? Iris setosa, Iris virginica. Or do we fail or pass the food inspection? Now we are at a multi-class problem. We want to understand if each of these pixels is a building, a block, a road, light trains, etc. So in order to create the system, obviously I have to learn from existing data, which you see here. For all these classes, I have already a training set which was annotated. So someone already did the job that you see here of saying these particular pixels are in fact a road, blocks, the soil, trees, etc. So we have a labeled ground truth here for this particular satellite image we can learn from. And based on the different classes, we have quite some data where we can learn from. And once we did this in the training set and used it for this, we can evaluate it on the so-called test set, which also is annotated, making it to, let's say, very important two terminologies here. In machine learning, you often would have a training set to learn from the data, basically in order to create the system, and then to evaluate if the system actually works well, you can train the test set. And once the test set is also saying it's a very good, let's say, performance you get there, let's say 70, 80% accuracy, rarely we are 100% in machine learning problems, in real life machine learning problems, then basically we are ready to put it to new unseen data set. Now, again, to understand that fully, we would use then the SVM in order to get basically to the best possible decision boundary that you can have with different classes in the multi-class setup in a basically higher level space if you combine it also with kernel methods. But let's say the maximum margin here suggests already from your gut feeling that this probably would be the best to do, because chances are that here the red point that would be otherwise, here you see this fellow, the new data set would be wrongly classified as green, although it's a red point. And the same is true with this particular fellow, where the green point here, if you put it to that space, would be probably also maybe wrongly classified or so. So in the end, that's what support machines do. And we have here different parameters in the job script. We have seen this here and there already in some of the earlier lectures. So we would have a SVM training, basically, where we then take the raw training data of a remote sensing data set called Indian, here as Indian pines as an example, but it really doesn't matter. But you see you have one executable for the training and one executable for the testing where we predict. In other words, these are two executables where we have to have two job scripts with. So I do first the training. The output of this training will be a model, which you basically see a little bit here, the trained model data, which we will have then available. We stick into the prediction and then it uses it with the so-called test cases here in order to come to the result of the accuracy. So this is essentially how you would combine this now with HPC. On the one hand, you have a, let's say, training and predict executable, two different jobs. However, the inherent idea of the SVM is basically not parallel. So we have now to think about a parallel algorithm that enables support vector machines to go parallel. Hence, we basically have to basically, merge this now with the techniques we learned from the previous courses, with MPI, etc. So before we go there, just a short, again, recap on all the terminologies I introduced. Right, so we said we have these machine learning models, which are important. There are various of those. You learned the logistic regression, the linear regression, and so on from the first part. Now we are at a different learning model called the support vector machine. However, it captures still the same essence of saying we have an in-sample data with the attributes in this vector X, given an output, Y, saying it's this or that class. We call that a labeled data set. Sometimes we also call it the ground truth here of this particular data item, which could be the pixel you have just seen in the satellite image. And here I know it's a tree, a tower, soil, or whatever. Hence, when you have this in-sample data set, you do something we call, you put them in different data sets for training and testing. And if you have a real machine learning course, you will learn you would also put different validation sets away to perform model selection. Because when you have, a model selected by yourself as a human, you put a certain bias inside, and then you don't use that data anymore. But these are more advanced topics which we can't cover here in the course. Still, they're very important for the performance of the classifier. Still, what you can do with this in-sample data given to us in a simple case, you just cut it. The way how you cut it is not that simple. Sometimes people would say put 10% training and 90% test, sometimes 20%, 80% test. Usually you would do, let's say, the training set may be smaller, but not too small. You still have to have lots of data to train from. So the percentage obviously depends on how much data items you have available, right? Because otherwise you have problems of really learning the pattern if you have too little training data. On the other hand, if you have just 2 or 3 data dots, which are your test set to evaluate your model, you can imagine that this is also not a proper test. So here, the question remains, where is the best boundary to put things in the training set and test set, where essentially you can see, if you're swimming in data, you don't have a problem. You do a large training set and have a very large test set. But in order to be confident about your model, you want to have also a good test set, a big test set. And hence there's a kind of, race condition again, where you put exactly this interesting cut in the training data. And there's not a really rule that says it needs to be that. That's basically something you have to experience from data problem to data problem, really. Another aspect I wanted to emphasize in, just looking on the data we have is not the story of machine learning. That's more statistics. They want to explain the data. They maybe here and there want to do some, let's say, based on that evidence, explain something. We are always, as machine learners, much more interested in getting future elements right, future data. We call that out of sample performance, right? So here's an out of sample dot. I want to know as best as possible, is that a red point or a green point? Whereas a decision boundary helped that we talked about, but of course it was a linear decision boundary. You can imagine that this is not really doing the job always. Hence we have other models like SVMs. If you put them with, kernel methods like a Gaussian kernel of sorts, you will come to very nonlinear decision boundaries, basically in the higher level feature space, as it is called. But still, the key idea remained the same, to differentiate future points right, which is so-called the generalization ability of your machine learning model, right? How good it is really generalizing well to unseen data, to new data points that I have here as an example. In other words, also, if you look on the data set you have, in the in sample, you have always the X and the guiding Y. When this new data set comes, or the new data set item here, it is just an X. We don't know the Y. The Y should be now determined from the machine learning model. Hence, you would have mostly, especially in this kind of, let's say, supervised setup that we said, a training set and then a test set in order to evaluate it. Now, looking from this a little bit more on a perspective now of saying, okay, now we have all this terminology. Now we talked about all these models. Where does HPC now make a difference in this particular, idea? And again, when you think about the overall approach, what we discussed about, just put it here in different blocks. You see the training examples are still there. That's what we discussed here. For instance, different pixels, having a guiding Y of saying, an example here, what is a land cover, but could be also the ones with the flowers. It doesn't matter. So this is what we always have, and that we must have. That could be, of course, already high demands in storage. Hence, a HPC center here can make already a big difference for big data. Especially satellite data becomes much more better with better sensors every year. And of course, with that, of course, also the terabytes it needs to store becomes more and more. And probably in the future, we will see there also exabytes and much more bigger storage requirements. Hence, here is already a demand for HPC, and basically also when you think about data centers in general. Now, what we learned was basically then in the other part one, particularly, we had this kind of hypothesis set where we said our hypothesis was, saying this should be the learning model of the perceptron. And then we had this perceptron learning algorithm, right? That basically based on these training algorithms did some final hypothesis of saying there was this interesting line that we could find that actually differentiates between the green and red points quite nicely. And this is then our final formula F that we report. So in a way, how you can abstractly see this is we want to have a target function somehow approximated or learned. Hence, it has some links to statistics with, basically saying it's something like function approximation. But we go a little bit broader in this in machine learning usually. And with this, we always have to assume a certain probability distribution. That is essentially what we remain a bit like the pattern, right? The important thing is that we don't need to know this. We never know what is the target function that actually we're creating these training samples. And we also don't know exactly the probability distribution, right? That gave rise to these numbers. Also, here are some differences to statistics. But still, we would assume a probability distribution on it, because otherwise we would probably have no pattern, right? If you now put Netflix ratings to suddenly, let's say, Apple ratings or things like that, which are basically from a different data set on X, the probability of maybe viewers will be different and so on. Then you have already a biased data set, which doesn't really help. So we assume somehow that the probability distribution that gave rise to X data is basically something which should be the same, and we don't need to know it, but we assume on it. And this brings us to something we call probabilistic learning models. So also a very interesting part, because essentially what we see here is a little bit that learning is not really possible only in a probabilistic sense, mostly because we see sometimes that the same X gives us a different Y, as one example, which is not anymore a function, right? Not a deterministic function. So by putting a probabilistic assumption above it, we can say that learning or machine learning more generally is so-called PAC, probabilistic approximately correct learning. But this reflects the learning theory I was mentioned that you basically have to usually go through if you do a machine learning course. It starts usually with a couple of lectures really identifying these elements. And then also think about the capacity of the model in the Wapnick-Chevonenkel's dimensions and so forth that we can't cover here. For us, more importantly, is that this is your toolbox, right? You always have the hypothesis set as your toolbox where you can pick from the candidate formulas of sort, where you say we can take a logistic regression, we take an SVM, we take a deep learning model, or we do basically just a perceptron. The perceptron is a model, and it has a perceptron learning model associated. It's two different things. The SVM has basically is a model, And what we use is quadratic programming. So you would always basically have different, let's say, learning models or optimizations really where you do the learning algorithms in order to make something work. And we see how we come back to this then when we have deep learning, artificial neural networks with SGD, stochastic gradient descent algorithms with learning. And many of these learning algorithms in one way have relationship to optimization techniques. You will learn this also in subsequent lectures. But of course, these learning algorithms now, when it's not perhaps a perceptron, but already with the SVM, we see significant improvements by using HPC here, because this learning iteratively through this data set again and again and again can be quite computational expensive in order to come to the final hypothesis, right? Hence, particularly here, we see also HPC helping a lot. And of course, in order to understand where we basically get better in the model, there's a so-called error measure, which essentially means we evaluate the model once we've gone through the training examples and then see, does the error improve? If not, we will change a little bit the model. Then we go again through it. And through iterative learning and taking this error measure, we can improve the situation based on the different learning models I pick. And then what I said in the beginning, we are actually able to learn an unknown target function really, which is in a way more a distribution. As I said, we have a probabilistic assumption over it, probabilistic of y given x, because we say that sometimes, unfortunately, machine learning, you could maybe look the same movie with the same x attributes, but people rate it differently, right? So we have to learn something which is not really a function, which makes it more like a target distribution. But by doing iteratively these aspects I just explained, it is able to do so, although we never knew what the idle function was in the beginning. This captures another idea of machine learning that we discussed. And the computing time and training time that we learned now is a bit loaded in machine learning because you can train too much, right? If you just take the same data again and again, and this is the error measure I just discussed, you knock down the error. That's what we do in machine learning, right? In order to achieve basically error in sample that is lower, that is a training error. So that's your goal. You can track this and see I'm getting better and better and better. Now, the tricky part, unfortunately, is that once you start learning, you start memorizing as well. So by doing so, you can imagine that you so-called overfit basically the problem by, in a way, memorizing already and knowing too much about the problem, so that actually your error out of sample with new parts will go up, although your error in sample is quite nice, and you come maybe to very nice decision boundaries, which are very wiggly curves or so, perfectly tuned for this particular data set. And once this new fellow comes in, it will be here and it will be out of sample performance is very bad, right? So hence we have here, if you train too little, you have a bad generalization capability of this classification model. If you do too much training, you overfit. And this remains to this HPC part. You cannot just throw HPC on it and say, yeah, we just, do that for a week in HPC. We have computing capacity enough. So let's train the classifiers for a week and all of them will be 99.9 performance. That's not possible. And the problem relies not in the computing part of it. It relies in the inherent, let's say, algorithms which are there. Because the approach that we have here has many side effects. It actually learns noise. It learns different aspects where we have to perform regularization. And then also what we learned, we have these different parameters of these models. Like in the SVM case, we had this two. I was discussing cost and the kernel parameter, basically. And we have to pick them also. And this introduces another, let's say, bias in the data or in the approach, which we have to do much more systematically using validation techniques. And validation, the purpose is there to really do proper model selection. And this is also loaded. If you have too little data, you cannot just put deep convolutional neural network, for instance, on it, because there, basically, the capacity of the model will quickly be, basically use all your little data and has nothing to learn from. So also there, the model, let's say, type of the model is also related to what we see here. And these are more advanced, let's say, techniques where at least every machine learning expert should know about validation and regularization. If you don't know about this, you're just still a beginner of machine learning. So you have to study validation, regularization in order to properly use machine learning techniques. And by doing validation regularization, we enable something that the generalization error also by iterative learning follows suits. Like you see here, it actually follows the performance. And by regularization and validation techniques, the chances are much better to actually follow suit here, also when the training time is too much. And by finding this sweet spot is, of course, a whole set of techniques that we have to talk to. And to understand a little bit the problem with this validation and so on better, you can imagine that we have this training set we had before. But the problem is that nobody tells you, should you do an SVM, should you do logistic regression, or what you should do, a deep neural network of sort. So hence the human has to pick this. And every time a human influences the decision in machine learning, we introduce a certain bias into this model. So we train, of course, obviously all of them with the training data. We get some hypotheses out of this hypothesis set, which are particularly suited for this model. And we have a validation set where we can validate in all these different models in order to get so-called unbiased estimates, right? Pair model. And that's not a problem so far, because yet I didn't pick one. I just try them all out. The trouble is exactly in this particular part where now the human comes and says, well, I see based on this data, this is the best performance, so I pick my HM star, which is my finalist, which I find best because obviously we see at some point in time that the performance is just the best. By doing this decision, we call basically pick the best influence and optimistic bias in the data set. It is problematic in the end for machine learning, which is an automatic learning from data. What you would then use, you decide on this model and put basically the data in the pot from the validation set. And if you swim in data, you would just throw it away and don't use it anymore, because then the bias in the data set of picking here would be also away. But because in machine learning for scientific and engineering problems, we often don't have that. We don't swimming in data, especially not in labeled data sets. We basically put that back into the pot and swallow the bias a bit. But by basically doing this, of course, with the whole data set, chances are that the impact of the bias are not that dramatic. But you see really with other techniques like cross-validation, which tries to counterfight this, you get much better modeling again out. Or if you have very big data sets where you can throw away validation sets that you used here in order to find the best model for model selection, and you throw them away, still have enough data really to learn, which is independent. And then what we didn't discuss here, you still have the test set in order to understand if, basically a generalization follows suit as well, right? Which comes now here. You see here, we have the final training and the GM star, and this is the final hypothesis we report. We still have to run through the test set, which is not basically shown here, basically in this particular graph. In order to counterfight these biases and also to, let's say, more systematically also now use parallelization, where really there are lots of offs in this cross-validation. I'll show you some numbers later, where you have a 10 cross-validation. And what that means is essentially you basically do, you train on 9 and validate on the 10th. And you do this iteratively by doing so-called folds in the data. Now you take basically this one fellow in again, like D4, and then you take D5 out, for instance, and learn on this. And by doing this 10 times iteratively, you basically have a better distribution of all the different classes in the data sets. You have a better representation, by doing this different folds. Hence, the best what you can perhaps do would be a one fold and then train many times on this data set. But obviously, this would mean you retrain again and again and again, and would cost a lot of resources. Hence, it could be still the best accuracy that you get out, because you have the bias impact and then also the class distribution quite good in the training examples, and then also in the validation set. And this is what you would do if you're not swimming in data. So if you cannot afford to really throw away your validation sets of sorts because your, let's say, labeled pixels for satellite images, as an example, are not that many. It's usually very time consuming or cost consuming, or have high costs, to really, do this pixel-wise annotation of data sets. Think about the human brain when you have very large images of, let's say, brain cuts, and you want to have every single pixel on those saying it's particularly this cortical layer or that cortical layer. It could mean hours of students annotating this. And of course, these are experts. It means you take away lots of expert times. Hence, we have often more patches, more smaller patches, which are labeled in order to do inference on the rest of the data set. And here you see the impact, basically by forming cross-validation on high-performance computing, also combined then doing the parallel computing approach. We basically discussed in one of our earlier lectures, if you remember, we discussed already the PSVM, which was a source code we basically took, which was not really created by experts from parallel computing, more from machine learners or statisticians. And there, of course, it was not really scaling well. We had to, let's say, massage the code quite heavily. You see here, there was this iterations of MPI broadcast and for loops that we then put all together, or the typical problems of using, again, a broadcast in loops in order to have this kind of details computed, small sums, and then actually distributed that again with a broadcast. You can do an all reduced, just a one-liner essentially, instead of all of these or all of these. And we also sent actually some other tunings, which was a very problematic load balancing aspects when you use this MPI collectives, and what we have seen before. The amount of data that was basically done was that the processor 1 got a little bit of the data, processor 2 got then actually just double the data, and you see a kind of so-called linear increase over all the processors instead of doing a proper load balancing across all the different processors. Since processor 1 almost has nothing to do, while processor 4 was basically heavily used. And you see here then, perhaps a bit smaller, we changed this with the load balancing scheme to a much more, let's say, balanced setup to take away some work from the others down here. And basically then you see processor 1 is redoing the work then here, and processor 2 is redoing the work here to come to a much more balanced setup of all these processors. And with this, we were able to scale much higher. Still, it's of course with sequential minimal optimization limited in its, let's say, most sequential parts. So we cannot do much more of scaling here. But by using already 128 cores here, we already outperform, let's say, typical serial tools like scikit-learn, or let's say smaller libSVM oriented approaches in MATLAB or so. So of course here we already can significantly speed up, and let's not forget we had also memory access problems through this. Also here, by having HPC machines, you often have much more memory available to work on, right? And with this, you already, of course, can also scale up much nicer with this tuned scalable code. And in the moment, I will say just bluntly here in the lecture, we believe we have the best scaling SVM code right now. And if you don't agree, also here in the YouTube lecture, please send us a message. We are scientists and open-minded, of course, to collaborate if you think you have a better tool in SVM. However, we tuned that significantly and came to some conclusions that you see here, compared actually to MATLAB executions that you see here. We have here a scenario in remote sensing, so the data itself doesn't matter here, just let's say the performance matters, right, that we got here. You see here a SVM, which has a so-called gamma here as a kernel parameter, and the cost of how much error you allow. And these are configuration items you don't know. These are kernel parameters, 2, 4, 18, 16, etc. You have to pick. And these are, the cost you want to allow. And what you in general want to achieve is the accuracy. So you see here, by identifying this table, you have to do every little entry of the table in order to understand that actually the combination of kernel 8 combined with allowing error of 100 is 77%, which is the best performance you can get. In order to reach that, you have to do all of them, right, in serial fashion. That's what basically you have to do in MATLAB. And it shows you here what that means. In MATLAB, you have 14 minutes to get the best one, but as you don't know what the best one is, you basically have to go through all of these different runs, which could be sometimes really long. And the long story short is essentially you would have something from the best parameter, which took you 14 minutes in MATLAB, we can do this with a PSVM, the same algorithm, the same approach, but just in parallel computing, with a parallel algorithm, we can break this to 1 minute, right? And this is just the best parameter set that you don't know. If you now take the whole grid, and we refer to this as the grid search of parameters, right? You see a grid, and we have to identify the best combination. The whole grid search here takes 9 hours in MATLAB, roughly. And what we can do with parallel computing, we break down this search for parameter spaces to half an hour, roughly. So, and this is, of course, a key benefit for machine learning in general. Also, you see here, multispectral remote sensing. Of course, when we have more bigger problems, you see 43 classes. You see classes which are mixed, really, with mixed class labels, multi-class labels. So it's not that easy anymore. You can imagine that the training here in this particular example where we talk about in lecture 10.1 will cost much, much more time. And there you would learn specific, patches from in basically this data set, and we will basically discuss why convolutional network will make their big difference in practical lecture 10.1, just as an appetizer. And in the subsequent lectures, you will see then, although SVM still makes sense as traditional learning models, when you have, let's say, low data set volumes, right? But if you have towards big data, you will see MATLAB, scikit-learn, they all will break because there's not memory enough. This is traditional models and so on. So you have to take HPC as a rescue, which means you have more training time. And with these basically models you can apply here, small or medium, and then really the cutting edge deep learning methods, which would apply lots of GPUs here in parallel and jewels. You have had a lot of training time, but with this, of course, you are able to get very good model performance and accuracy. And that's what we will do in the subsequent lectures of practical lecture 10.1 and 10.2, still saying random forests, SVMs, these are all learning models which we consider not deep learning. They basically still are very much used in practice today because they're also very, let's say, they're very robust techniques if you don't swim in data. We will learn basically in the next lecture more also about remote sensing and how we then use different, let's say, deep learning networks, where we will stimulate the same aspects we talked about today with this robustness of parameters, where SVMs have just 2. But here in this space of this deep learning, you will learn in the next lecture that basically we have lots of different hyperparameters to choose from as humans, right? And then on top, you have all these different connections. These are all, let's say, neurons inside, and we will make the connection to the linear learning model, in fact, also with first artificial neural networks and then deep learning networks in the next lecture. But all of these needs to be learned. And then the hyperparameters influence, of course, is learning again. And this is something which brings us to very many options of how you create a deep learning network, which is not at all obvious how you choose them. And although you have some recipes, we will learn particularly also from Rocco, one of my PhD students in this particular lecture 10.2, where he talks about ResNet 50, which is, let's say, a certain recipe of how you can use a deep learning network with a particular problem. And we will learn there already that essentially we can do huge speedups with GPUs in order to learn 25.6 million of trainable parameters. And we will go there also in this particular lecture and learn the case why then, of course, HPC makes a big difference. In the area of distributed training with multi-GPU usage, there's a certain technology called Horovod we will discuss. And there's also deep speed today, where also Rocco will basically then show you why it's so successful using these models in machine learning and deep learning together with many different GPUs. You see here with 96 GPUs, we reduce the time per epoch, but also there we will have much more details in lecture 10.2 and how this works. Just finally, short pointers to clustering. No groups of data exist, that's what you know, with similarity measures. And by now you basically have seen the DBSCAN clustering algorithm a lot. And there are a couple of parameters that you have here, like the minimum number of points that constitutes a cluster and the epsilon neighborhood. So how many around you would consider basically be directly density reachable and so on. At this, something where, the concrete details of these algorithms, it's not so important to understand, but you see that machine learning and HPC can, not only, of course, significantly speed up classification, it also significantly can speed up clustering. It needs a different algorithm, as you already know. It's our HP DBSCAN that I had in all different classes already, so I don't have to go back to it very much. I think you get the story by using this. Also in your assignment, you will see yourself how the speed up works. And we have seen it basis everything we learned in the early lectures with Harlow regions, with basically doing the load balancing scheme, with perhaps even use OpenMP and MPI, and both at the same time, which makes it a hybrid to the best performance, almost linear, and so on and so on. And of course, it's not related only to our DBSCAN that we had for the Bremen dataset with point clouds. You can do it also in neuroscience. Here, as I said, in the images, the kind of cells that have different, let's say, Euclidean distances, there you can cluster in order to identify different cortical regions, for example. Long story short, machine learning, clustering, classification algorithms can benefit enormously these days, not only because of the sheer amount of data, also if they are really parallel computed and parallel algorithms, then HPC can really help a lot. And also you have seen on the parallel file system, using it with HDF5, for instance, can significantly also increase performance, not on the algorithm level, but on the IO level as well. Finally, to understand the DBSCAN maybe better, I provide you with a small example here of DBSCAN, where essentially you see how that works better.
Only relies on two parameters, epsilon and minimum points. Epsilon is a distance parameter. You can think of it like a radius from a given data point that broadcasts out in all directions, forming a perimeter around the data point. Minimum points is the second parameter you must specify. Before we get to that, I'll define two key terms. The first I'll call the starting point. The starting point is a randomly selected data point that will attempt to start a cluster. In this image, the green circle represents the starting point. The second term is core point. Core points are data points which fall within epsilon of the starting point. In this image, all gray circles are core points. The white circles are not core points because they aren't within epsilon of the starting point. Minimum points is the minimum number of core points, including the one starting point, that must exist for a cluster to be formed. In this example, there are 7 points within epsilon of the starting point, including the starting point itself. Thus, if minimum points is set to 7 or less, a cluster would be formed. However, if minimum points was set to 8 or more, these data points could not initiate a cluster. Once a cluster is formed, that cluster can continue to grow. Each member of that cluster will broadcast out their own perimeters, looking for new data points that could join the cluster. In this step, you can see the core points did in fact find new members to join the cluster. These points have been made blue. All the blue points in this example are considered border points. This means they are part of the cluster, but are not within epsilon of the starting point. Now these new members will cast out their own perimeter and search for even more members to join the cluster, but in this case, they don't find any. Because new members are not found, this cluster is finalized. I've turned all members of the first cluster blue. However, you will notice there are 3 white points still unclustered. Now we will restart the process by randomly selecting one of the remaining unclustered points. I have again designated the starting point green. I won't run through the steps again, but this iterative process continues until every unclustered data point has been looked at. As this algorithm finishes running, it may eventually form multiple clusters, as seen in this example. But note, this red group could only form if the minimum points was set to 3 or less. Now that you understand how DBSCAN works, I'll show you a start-to-finish visualization of the running algorithm found at naftaliharris.com.
Okay, and here we have our clustered smiley. I think the idea the recursive strategy really of the algorithm becomes pretty clear with the epsilon neighborhood more better in a video than I can ever present in slides. And I guess you have the idea that now when we crunch down the space of the smiley into many different domains, with a domain decomposition and apply different processors, they can do the same thing and just merge the results. The merging is of course a bit elaborate, where you also have to adhere to the clustering rules, but then can of course significantly speed up the process also in this clustering. And the next time we will talk much more about more cutting edge algorithms with deep learning, making the connection to first so-called artificial neural networks, then extending them to the new deep learning ideas, when then really Rocco goes for the deep distributed learning of these with many, many GPUs. And we basically see us then.